email about homework and this workshop that starts tomorrow. So you haven't known this, but you will. But so there's a workshop that's, tomorrow and Saturday. And so I sent 3 links on the email to
He goes on Canvas, but it was email. I saw it on Canvas.
That's amazing, because I went and sent an email, and it didn't go. That's bad. That's really bad. I don't understand. This has happened before, and I don't get it. Oh, hello, Jonathan. Oh, well, I'll have to sort this out. But anyway, there's a assignment 1. There's my lecture notes for like last lecture and lectures to come, and also this PDF, or maybe a preliminary version. But I'm not sure if it was the most recent version. No, it wouldn't have been, I don't think. The schedule is now finalized. And somebody here is interested in deep learning. There's a talk. Somebody's interested in Peter Glynn, who's my hero at Stanford, works in simulation and all sorts of different areas, stochastic approximation. Stochastic approximation is the foundation of all these learning algorithms, like Q-learning. We've got 2 experts. Peter Glynn is coming, Yvat Chaudet, who's coming, and unfortunately Eric Moline, who's an amazing colleague, he can't come. He's not well, so he's going to miss. But there's wonderful talks on communication, computer science, and statistics, and please come. Again, it'll be great. So anyways, there's handouts here. I'm not going to pass them out, but you can take a look after lecture. I'll be vandalizing the CS building with taping these up after lecture. So okay, so that's one thing. So where were we? So we were looking at the uncontrolled deterministic system, and again, the motivation is that deterministic systems is geometry, things are a lot simpler, and when we get to the stochastic case, the equations are identical. And there's a little bit more technicalities in trying to prove anything, but the equations are the same, exactly. Now, this Lyapunov function is sort of the fundamental Lyapunov function in the stochastic case. So you don't actually see this in a deterministic case very often. You see this very often with that constant 0, but not that. But in order to make this look like the stochastic setting, I'm going to introduce some notation right now. So when I write dv evaluated x, I'm taking the function v and I'm transforming it to get a new function, which is the grad of v dotted with f of x. And in stochastic processes, that's called the differential generator. Okay, so we're not going to be looking at controlled diffusions because that's a little bit outside of our, intelligence range. This is too much machinery that we'd have to develop. When we go to discrete time, instead of a derivative, it'll be a difference equation, and it'll still be we'll still call it a differential or a generator. All right. So it's just notation, but it's really nice notation because when you see this dot product, you have to remind yourself, what the hell does that come from? But when you see differential generator, it always means the same thing. It's a derivative. It's what we said before. dv of x is defined to be equal to the derivative with respect to time of v of x t, evaluate t equals 0. Oh, actually, t equals t naught if x t naught is equal to x. This thing here, this looks like a bunch of gobbledygook. Look at all these symbols: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And when you write dv, it just always means that. Although if it's stochastic, we'll have to put an expectation sign around it. All right, notation. What's that? No x. I mean, so given a function v, dv defines a new function. How do I define it? Okay, and so for any t naught, if x, I'm saying that if I watch a trajectory and I see it pass through the state x at time t naught, then dv of x is just the derivative at that time. Yeah, that's what it means. I was about to say, obviously, the way I defined it before was the derivative t naught equals 0, and x of 0 was x, the initial condition. You know, and that's maybe a bit more natural. Okay, is that clear? Okay. All right, so this is the kind of notation, this sort of compact notation is really powerful, believe it or not, to help us think about things and to see the commonality between all the different frameworks. I mean, especially the bridge between deterministic and stochastic theory. And it takes some time to digest, but you're going to have to, you know, internalize this notation. You know, it really is important. Through the whole course, we'll be using this kind of operator notation, and it'll help to, it's like I don't know. I actually watched my own lecture from 2 years ago when I taught this last, or 3 years ago, and I remember saying, "Why do people find this so hard?" You can actually see this. You can see all the YouTube lectures from 3 years ago, and it is just like a language. You know, I mean, you know, basically the concepts are really easy, but you've got to learn this language, you know, and these, and if you say, forget it, that's math bullshit, I don't have to learn it, you'll never learn anything because you won't know the vocabulary to be able to go further, you know. And I wouldn't be able to consult from Motorola or United Technologies or Google if I didn't have that language, because it's the language that people in industry use, believe it or not. It's not just, I'm not just trying to be a mathematician, okay? It really is shorthand to make things more efficient. You know. I started out that way, by the way. I mean, when I was an assistant professor, my first love was math, and now it's not true. I think that I like applications more, but I wouldn't be so valuable in industry if I didn't have these abstractions. All right. Maybe I'm overselling this, but anyway, I just know that there's always 20% of you who just say, I don't need to know this. The professor just is in love with math. It's not true. It's really not true. You really need to know this if you're going to get further. All right. So we saw that we saw last time that by the fundamental theorem of calculus, we found that that the integral from 0 to t of c of x of t dt was less than or equal to v of x of 0 plus t times eta bar. All right, we saw that. And when you see this, it's natural to divide both sides by capital T and talk about the average cost. But again, you'd never see that in a deterministic optimal control course. What you would see is the total cost. Okay, so if eta bar is 0, this term disappears. I've got a uniform bound for all t. I can let t go to infinity, and I get that. That is like the thing, like Jacob Hammer in the EC is teaching optimal control this semester, and this is what you'll see every single day. You know, every single day for the entire semester, you'll see this and how to analyze it. So we saw that last time. So some language. I'm going to call this Poisson's inequality. Nobody else calls it that. Well, that's not true. Peter Glynn will be using that kind of language. You know, he would use that sort of language. And because of the fact that dv equals minus c plus eta bar is what's called Poisson's equation for Markov processes. Okay, so this will turn out to be something that'll be used in stochastic case again and again and again, and there's a name for it. And it's the same, if you've seen Poisson's equation, you know, in physics or something, it's a generalization of that. I mean, so there's a generalization because it's an inequality, there's an equality in a Poisson's equation. And in in the theory of PDEs, D is a Laplacian. It's a second-order differential operator, and here it's a first-order. And it's a first-order differential operator here because we're looking at the deterministic case. Okay, so anyway, for those of you who've taken physics or looked at Poisson's equation, I want to, before I move on, I said I was going to give you in 90 minutes a complete theory of non-optimal control. We sort of will, I mean. But before I do that, I want to give the converse theorem. I realize it's really useful. So here we said that if this Lyapunov condition holds, Poisson's inequality, with eta bar equals 0, then the total cost is bounded. There's a trivial converse, you know. And some of you have seen it probably. Anybody seen it? No? So suppose that the total cost is finite valued. For every initial condition, this is finite. Okay, suppose this is finite for every initial condition. Can anybody here think of a Lyapunov function that would satisfy Poisson's inequality? What function would it be? X squared? There's only one function on the blackboard. And it's not v, because we don't know what v is. The question is, what is v? And it's not c. That's another function on the blackboard. It's only one other function. It's got to be something to do with the system, right? Well, yeah, so I could tell by you're nodding, you know the answer. Nobody else seems to be nodding with, oh, it must be this. You know, but so then v equals j. Now, j. Now, you'll say I'm cheating because I told you that v had to be continuously differentiable, and we can't even tell this is continuous. You know, so I'll have to put in a caveat. Okay, if this is continuously differentiable, then it'll satisfy that Poisson's inequality. Instead of an inequality, I'll have an equality. And it's trivial. It's just look at the system. I start out with x of 0. You give me an x. I say, okay, I'll start off a simulation. You know, I look at a simulation, and I remember what the differential generator is. I want to differentiate along this solution. You know, remember I want to look at, you know, the goal. This is what I call dj of x. All right? I take j of x of t, I differentiate with respect to time, set t equal to 0, you know, and because I assumed x of 0 equals x, that's the differential generator acting on j evaluated at x. All right. Now I'm not going to use the chain rule because I don't know anything about j except that. That's the definition. But when you take derivatives, you know how to do it. You know, you look at j of x of, you know, we know how to differentiate. let's differentiate. So we're going to take an intermediate time here. And we have to consider to differentiate, we have to understand what on earth is the total cost from that point. You know? So we'll take the total cost from that point and we'll subtract off the cost there and divide by Tm. You all know how to differentiate, right? You know, I forgot to put that in the handout. But to differentiate, you know, you look at j at some time minus j at, you know, this time 0. You divide by Tm and let Tm go to 0. So first we have to understand what this is. But does anybody know what this is? I mean, I was looking at the total cost starting here, integrating along this curve, the cost. You know, but now I'm starting here and integrating forward.
It's the same integral, just instead of 0 to...
Yeah, that's the beautiful thing about all this. That's why control people get so excited, you know. So in economics, is competitive equilibrium theory. It's so simple and it seems to imply so much, and so economists get, you know, all horny, and control theorists get horny over this. That you can say something without anything. You know, it's just immediately obvious that the integral of the cost over this whole trajectory. Well, if I just ignore the first bit, I'm only integrating from Tm to infinity, right? And so therefore, if I look at j of xtm minus j of x, I mean, so the other way around, I mean, yeah. Yeah, that's right. So when I differentiate, I have to look at the difference divided by Tm, all right? So I'll end up with this minus that. So I'll get the negative of the little integral. And QED, yeah, so this is a continuous function of time, right? And I'm averaging that continuous function of time. Yeah, I should have said C is continuous, okay? C is continuous, C is continuous. All right, otherwise I'll be in trouble. If C is noisy, then I don't know the average will be C of x0. So I let Tm go to 0, this thing is going to converge to minus C of x, you know? Okay, so where is it? Right there. You know, so what I've shown is that this derivative is equal to minus C of x. All right? Let's write it down again. And really it's true for any time, okay? I mean, I'm saying that evaluate t equals 0. You know, and I'll do it if you like. That's what we prove, but it's true for any time, obviously, just because it's the same formula. All right. So the technicalities that come about in this field is to prove that J is smooth, and so that you can actually express this as a gradient of J times f of x. You know, that's the technicality. But the fact that this derivative is minus C of x is just nothing. It's a fundamental theorem of calculus. Again, it's nothing. Is that clear? It's just a fundamental theorem. It's just baby math. But again, proving J is smooth, that takes muscle, and that really is. And it's much. Well, I couldn't say that. It's hard. It's not true either. I mean, there's examples. It's really easy to come with examples where J is not smooth, and yeah. And what you do in the stochastic setting is you give up on differentiation. You just you don't ask for derivatives. You look at integral forms of the same equations, just so you can avoid these technicalities, because we don't need the representation anyway a lot of the time. So. All right, so I just wasted 20 of my valuable minutes to fulfill my promise of deriving all of optimal control in 90 minutes. So now we have to do it in 70 minutes. What's that?
Why is J coercive?
Oh, why is J coercive? Oh my God, you're right. Scheiss. Oh my God, you're right. So there's two gaps. Thank you very much. Yeah, I forgot about that. I'll use shorthand. Is J continuously differentiable? You write C1 for that. You know, that's hard. And 2, is J coercive? We didn't check that either. And so you need conditions. Yeah. So if C is coercive and if the function is Lipschitz, you know, then you can prove that. You know. Yeah. Yeah. But yeah, thank you very much. That's a good point. Nobody's ever asked that before. Yeah. So yeah. So this is pretty easy to demonstrate it under very, very mild conditions on the system. But this is damned hard. Yeah. As you can imagine. I mean, it's yeah. And in some ways, it's harder for deterministic systems than stochastic in a way. It's yeah. All right. All right. So shall we move on? Anything else? Crystal clear? Okay, and so I'll make these notes available to you. I'm revising them. You know, this is like 2 pages or 3 pages for deriving the HDB equations. And I'm going to include this. I'm going to revise the notes because if you really did understand this perfectly well, what I'm going to do next is just a trivial extension. You know. All right. So if you didn't understand this, tell me. You know, you won't understand another word. Yeah. Yeah. Please ask questions. Yeah.
I don't think I understood so like J's
yeah.
coercive.
Oh, I'm just. Oh, yeah. Go on. Actually.
I just didn't like.
Oh, in our original theorem, we said, suppose that we have a continuously differentiable function that's also coercive, satisfying this bound. So we only showed that this holds. We didn't verify these other conditions. So we don't have a complete converse. That's all. Yeah. Yeah. So it's just to make it an if and only if statement. Yeah, it takes some more work. Yeah. Okay. So optimal control. So, okay, so if you have to have an optimal control, first you have to add a control. So there's an input here, which just say takes values in Rm. So again, x of t is in Rm, Rn is before. And of course there'd be conditions on f and all that. I mean, I'm not saying that f is going to be, for a solution to this to exist, you need conditions. You know? So f is going to be Lipschitz continuous in x, things like that. Take another course. You know, I'm just trying to give you the main concepts. And then we have a cost function as well. So then we had a c of x. Now it's going to be a cost function of both state and control. Okay, so this will be a continuous function of its arguments. It's going to be continuous, non-negative. I mean, and you need more conditions. Again, I just want to give you the main ideas. We'll have the same thing as before. Maybe it's a little bit subtle. No, it's no difference. There's no subtlety here at all. So I'm gonna put a little subscript here on the u. I don't like that really. I don't know. The notation's not perfect. Okay, but anyway, I'm gonna write d sub u v of x. Yeah, again, I don't love the notation. It won't slow us down too much, but that's exactly the dot product before. It has the same interpretation. It's the derivative with respect to time of v of x of t, and I'll say evaluate t equals 0, and with x of 0 equals x, and u of 0 equals u. Assuming everything's continuous, assuming x of t is continuous and u of t is continuous, which we'll assume. That, the x of t solves a differential equation, it's continuous. U of t is going to be a continuous function of xt. They're all continuous functions of time. All right, and so we're going to have the same interpretation as before. All right, and if you take a course on where it's gone now. We're going to for any input u. And I don't know why I don't have an x in there, but in my notes, I don't have an x. And it's silly not to have the x dependence. See, in my notes, I can have boldface. And this u would be a boldface because it's a whole trajectory. So how about a vector here or something, or dots or something, to emphasize the fact that it's a whole function. So u is a trajectory, all right, and I plug in a trajectory, and I get a cost. And this will be infinity most of the time. Yeah. Yeah.
Confused on the notation.
So yeah.
Like x naught equals x,
yeah.
That's not the whole trajectory.
No, that's the initial condition.
So, okay.
Yeah. And this is just, that's right, that's why it really is bad without having to be able to do boldface on the blackboard. U of 0 is u, which is just a vector in Rm. And I'll just say u bracket, meaning the entire function of time from now to infinity. And I've got a function of two variables, x and u. and there it is. And there's my cost for a particular input. And the goal is to minimize this over all functions. All right? And of course, for this to be finite, you need conditions. I mean, and we'll just ignore that. Just assume it's finite. In any class, the first thing they'll do is start with the linear case. And that's not good enough. You can't solve that unless you put structure in the cost. And so you have a linear system, quadratic cost. That's called the LQR problem. And you have to assume R is positive definite, strictly positive definite. Okay, so this is never 0 for any u. All right, but here Q could be. This has to be positive semi-definite. It could be rank 1, for example. It could be. It could be that. So an example is a rank 1 matrix. So V is a column vector, V transpose a row vector. Okay, so that's an n by n matrix. but all its eigenvalues are 0 except for 1, which is the norm of V squared. And if you look at X transpose QX, it's just V transpose X squared. So that's 0 for a lot of X. That's not a problem at all. But here you really need R positive. And the solution then, as you all know, is linear. So that's why people do this. Okay, and I won't tell you, K star is a gain you can compute through a horrible equation, all right? What's fun about this is that if you tacked on noise, if I put in x dot equals ax plus w dot, you know, if I could define that, some noise, the solution wouldn't change. The stochastics doesn't matter at all. You know, you put in randomness here, doesn't matter. So it doesn't change the control solution at all. And that happens a lot of the time, that, you know, you add noise and maybe it'll change the control solution a bit, but not that much. It's amazing. So that's something, a really important message, you know, is to not obsess too much about disturbances. Often their impact on the control solution is not that important. Their impact on performance might be huge, you know, but the actual policy might not change at all. And this is an example where noise doesn't have any impact. This policy is the same. If you add noise, make the variance bigger, who cares? It doesn't matter. Right. So we'll come back to that. But we're not going to get so lucky in general. We're going to find that typically we get state feedback. So star here means optimality. So there's some really nice function of the state, and you take that function of the state, it defines U of t. No memory at all. That's why we love state space models, because we can define our optimal input. The input that minimizes over all possible inputs is simply just a static function of the current state, just a readout map. And that's a wonderful fact. You know, without a state space model, we wouldn't get this beautiful, beautiful structure. Now, finding phi star, that's the topic of the next 40 minutes. And we will do it. Yeah, let's go a little bit further before we break. Okay. So you tell me what I'm going to do. So yeah. Okay, let's just define J star of x to be the minimum of all functions of time of J of xu. Well, you know, you know what I mean here. X0 equals x. All right. So for every x, you give me an x, I go and I minimize this over all inputs u, and I get J star of x. And I do that for every x in Rn. All right. I do that over and over again, and I will get this function. Yep. Yeah.
Question.
Yeah.
Is there significance that the x of t is also starred?
Yeah, but I want to say it's the optimal state trajectory. You know, it's a special. So there's an optimal input, and it gives rise to an optimal state trajectory, and you know, and so what we want to do is I want to compute phi star, you know, and to do that I'm going to have to think really hard. But it turns out I can use the recipe we use for stability and just apply it here directly to get a formula for phi star. It's pretty nice. And let's just, I think I'm going to set things up and then we can take a break. You know. So again, we've got x, which is equal to x of 0. And we did a beautiful job, you know, we're so happy because we've solved this problem. But we haven't because we don't know what this is, okay? But suppose we had. Well, this is this thought experiment. And J star of x is the integral from 0 to infinity of c of xt star ut star dt. And that looks familiar, all right? Now, that's what we were talking about when we did the converse theorem. We all agreed it was trivial. Well, getting a formula for phi star is epsilon less trivial. Okay? And so we're going to have a TM, you know? Because what we're going to do is we're going to get a differential equation for J star, and from that we'll get phi star. You know, it's exactly the same way. Okay. And the big difference here is we have this velocity vector here. There's a star there. You know, and we had choice of that. Now we have control. So we didn't have to go that way. We went that way because it's optimal. You know, we had a choice where we could have gone this way. The dot there refers to as a bad choice. You know, it's just going the wrong direction. You're going out in outer space when you should be coming back to Earth. So we have a whole choice of directions that we could have chosen, and this is the one that's optimal. So we follow this optimal path. All right. And I want you to stare at that for a while we take a break. You know, and just imagine how you would now, derive Hamilton, Jacobi, and Bellman's ideas. All right. I think it's a good time for a break. This will be fresh when we do it. All right, 5 minutes, maybe 10. Anyway, we'll see. Whenever, yeah, less than or equal to 10 minutes, we'll see you back here. And this is the thing. Now I know, very often, now people run up and ask me questions. I say, damn it, why didn't you ask me 20 minutes ago?